Greetings, everybody. Apologize for not being able to be there in person. I hope you all are having a great time there. This time of the year is one pretty good over there. I'll talk about Compute Express Link, like Hari said. Can you guys see my screen and hear me okay?
Yes.
Okay, all right. So let's get rolling on this topic. So agenda-wise, there are three broad sets of things I want to talk about. One is what I call load store I/O, where do they fit in the compute landscape. Then talk about CXL and how it has evolved and where are we at, where are we going, and finally conclude with call to action. So if I look at the compute landscape today, you pretty much have servers that are in racks making up pods, right? And then you got the entire data center full of pods, effectively any kind of. So this is the picture of a rack. You got compute nodes, you got memory storage chassis, and then they're connected through predominantly through networking kind of interconnects, copper for short distance and optical for longer distance. And we're going to talk about a set of challenges that CXL is solving, and that has to do with effectively how well do we utilize the resources in the data center, right? And how do we get more compute efficiency? How do we solve the memory challenges? All of those things. In all of these, what we will see is that the interconnects, they are very critical in driving warehouse scale efficiency at the data center level. CXL is based on PCI Express 5, and let's take a look into, as well as PCI Express infrastructure, and we'll go through some of the reasoning. So if you look at PCI Express, it has been there since 2003. Products have been out there. This is what you see here is the different revisions of the specification. These are the different data rates that we support with PCI Express. This is the effective bandwidth that we get for a 16-lane PCI Express link and the year where it was introduced, right? And every 3 years or so, and you will see, the numbers do vary, and some of them are compressed, some of them, go out a little bit farther out. It all depends on the demand that the ecosystem has, right? So technologies evolve. These are industry-wide technologies. They evolve based on the demand. Full backward compatibility. By that, what I mean is if you have a by 16 slot today in a platform, which is the 5th generation, let's say, and you purchased a PCIe card back in 2003 to 2004, it will still work in that slot, right? So that's backwards compatibility. By 16 works with a by 1. So all of that is guaranteed, right? And in terms of the way the spec is there. It is the ubiquitous I/O. It's there everywhere from your PC, your handheld, your smartphones, to your workstation, to your servers, you name it, right? I mean, it's there everywhere. And the way we do this is that it's one stack, one base specification, one silicon, but works across multiple form factors. And in general, the drivers for these speeds, among other things like CXL, we'll talk about in a minute. It's around networking, XPUs, and CXL is alternate protocol here, right? And memory is it's a big demand. So it has been more than now 3 decades, and this speed transition as well as transitions in terms of protocol enhancements on all of those things are going pretty strong. Right, so there's no signs of slowing down. So 7.0 we are expecting to come out in 2025 at 128 gig, right? Still keeping the PAM4 signaling and the flit mode encoding. So now with that background, let's look at Compute Express Link. And there are 4 challenges that CXL solves, and it has done that over time through multiple generations of the specification evolution. And I'm going to go through them one by one. The first challenge is around heterogeneous computing in a given platform, right? Within a platform, heterogeneous computing, and what it enables is effectively cache coherency for devices, as well as the memory that is mapped on the devices into the coherent memory space. So let's look into the picture here on the left with PCI Express only. And by the way, this model still works. It's and you will see that CXL still deploys the .io semantics is pretty much identical to the PCIe semantics. So the model here is, you got your CPU attached memory that's OS managed, that's typically coherent. And then you got your memory that is attached to the accelerator. These are, runtime managed, and these are uncacheable memory. Effectively, cache coherency does not go beyond the CPU, and they're still load store. And the way it works is there is producer consumer semantics, ordering semantics that effectively everybody enforces, and especially the CPU is responsible for making sure that the producer consumer semantics on the PCI Express side, ordering semantics, messes with the cache coherency semantics that exists on the CPU side, right? So, there are direct memory accesses going on. So if you want to access something, you get that data structure, you process it, you send it back, and so on and so forth, right? And that's the way it works. And that works really well for wide variety of applications. Absolutely, it's wonderful. Now, there are an emerging classes of applications, and we'll see some of them in a couple of slides, that want finer grained interaction between these accelerators and the CPU, as well as amongst themselves. So they need the coherency semantics. So what do you do for them? And by the same token, the memory that might be attached to them, because if you participate in cache coherency, also your memory needs to be mapped into the coherent memory space. So this is where CXL introduces the notion of cache coherency. It effectively treats memory as a global entity that's seen the same way by everybody. Doesn't mean that the memory map IO region goes away, the non-coherent part, but it's the choice. It's no longer just restricted to the memory that is attached to the CPU, right? So it's your choice as to how do you map your memory. So that's the first problem statement, heterogeneous compute, because as we see, and we have seen today, it's a world of accelerators, right? A lot of people are running purpose-built like AI accelerators, GPUs, all of those things, right? And they need finer grained data processing. So that's basically what CXL brings to that table in the form of cache coherency. So that's the first challenge that we addressed. Second challenge is around the system memory challenge, and especially in the context of AI, this is becoming more and more pronounced. If you look into the DDR off package, DDR is the standard way in which we are delivering memory bandwidth. On package, it is primarily HBM, right? And this is an off package interconnect, so I'll just stick to the off package part of it. And by the way, HBM also has its challenges in meeting the demands. But off-package interconnect wise, if you look into the DDR, it's a multi-bus interconnect, bus-based interconnect, bus turnaround. All of those things are involved, and in there, if you look into the speeds and feeds, those are not going up that fast, right? I mean, after all these years, DDR speeds are 6,400 mega transfers per second, going to 7,200, and even that's becoming very, very challenging. And that's in spite of those DIMMs being very close to the processing element, right? They have to be placed very, almost next to the processing element, right? And those are wider buses. Of course, the advantage is that the latency is really super low, right? But so that's the challenge, is that with the memory bandwidth, it's not really keeping up on a per channel basis. So how do we solve that problem? We're solving that problem by adding more and more memory channels, right? So, in a CPU, we started off with, long back with just one memory channel, then two, then four, then eight, so on and so forth. It keeps growing, right? And it's about 300 signal pins for each memory channel. So packages are becoming huge, and this is just not sustainable in order to deliver the memory bandwidth that you need. So you will see that if you look into the CPU core count, even ignoring any improvement within the CPU within a package, if you look into the CPU core count, this is just your Moore's law or packaging technology. It's on an upward cadence, right? I mean, it's not just mainstream CPU, it's also all the GPU. So core count is on the increase, and if you look into the effective memory bandwidth per core, it's decreasing. So it's moving in the wrong direction. The other part of the thing that's happening is the leading edge of memory technology is getting more and more expensive. Because we are processing more, we need more memory in order to feed the beast, both from capacity point of view as well as from a bandwidth point of view. And the price is flattening out. So what that means is your cost of the memory as a fraction of the cost of the server of the platform is increasing, right? It's 50+% now. So second challenge is around the memory scalability. Sorry, was there a question?
No.
Okay. Second challenge is around memory scalability, both in terms of the bandwidth as well as the cost, all of those things. And that's what the first generation of CXL is solving. So what we see here is CXL, the first generation is a direct connect. CPU connects to a device, and CXL maps, as I alluded to earlier, the IO is similar to PCI Express. This is the regular DMA, the regular all the discovery stuff. Everything else is included, so you don't have to reinvent that wheel. But we added caching semantics and we added memory semantics, right? Very simple caching semantics and memory semantics. So the usages are, you will have things like an accelerator NIC, for example. There, what's important is, where does caching become important? One of them is that the NICs do a lot of more advanced atomics, for example, that may not be available in PCI Express. You can always bring it to PCI Express, but it takes about 3 to 4 years by the time products show up. But if you have your local cache, you can just do your own atomics and be done, right? You don't need to go through and make sure that every other CPU root port, everything else, switches, if you're going through them, have support for those. The other thing is around the PGAS ordering model, which is different than the PCI ordering model. So basically things get sequentialized, right? So you avoid that because you can prefetch things because of caching semantics, and you can complete them in the desired program order in the local cache. Second type is around GPU and all of those FPGAs. Here you have your own memory. So not only do you want to be able to cache the system memory, but also you want your memory to be mapped to the system coherent space. And that's why you need all three protocols. And the third type, which is the third challenge that I mentioned, is around the memory bandwidth and memory capacity expansion, as well as a tiered memory approach, right? To second level memory. So there you don't need caching semantics. All that you need is really memory semantics. The IO semantics is there for discovery and all of those. Now, how well does this do, right? If you look into, a 300 pin DDR, for example, right? Your bandwidth is around 50 gigabytes per second, right? Raw bandwidth. If you look into, for example, a by 16 Gen 6, which is available, right? And Gen 7, we are working on it, but Gen 6 is available. So if you look into a Gen 6, then a by 16 gives you 250 gigabytes per second of raw bandwidth. Okay, so 300 signal pins, roughly 250 gigabytes per second. How many signal pins are we talking about? We are talking about something in the range of 16 times 4, which is 64 signal pins, right? So you can see that there is already an order of magnitude difference in terms of the bandwidth per pin, right? There's no way you can compete with SerDes link in terms of the bandwidth per pin, right, versus a parallel bus. Now, the downside is, of course, your latency will be higher because you are going through an external with serialization, deserialization overhead. Okay, but that's again, people have worked through those, right? And in general, if you look into the CPU to CPU cache coherent link, that's about the same latency add that you get, and we know how to deal with that. So that's the second challenge, right? Is around the memory bandwidth. Now, the third challenge, and this is something we addressed in CXL 2.0, is around resources getting stranded in the data center. And here I give the example of memory being stranded. You can also make an example of, hey, some applications need 5 FPGAs, some need 3 FPGAs, some need no FPGA or GPU, pick your favorite accelerator, right? How do I, and what do we know about these tightly coupled system is that if something belongs to, let's say memory is a good example, right? If you have memory belonging to a particular server, it belongs to that server. Let's say, if I have a terabyte of memory here and this server has a terabyte of memory and I need an extra half a terabyte for a particular job that I'm running, There's no way for me to really borrow the half terabyte from this other server without going through a networking stack, right? And that defeats the purpose of very low latency memory access. So what we did with the second generation of CXL is we introduced this notion of, and the CXL switch, it may be a physical switch and it may not be. You can always have a device connect to multiple servers, right? So that way there is no physical switch involved. But it's easier to explain things in the form of a switching infrastructure. So if you have a pool of memory, then the idea is that, well, I don't need to oversubscribe my resources during when I construct my platforms. I don't have stranded resources. I will construct it for whatever is a reasonable size. And occasionally when I need more capacity, I'm just going to go over to the pool and get that capacity. And that helps in that regard. The other things that we did are around, we have to define fabric management, because this is the first time tightly coupled load store interconnects are going across an infrastructure where it interacts with, not directly but indirectly, with other servers, right? So you want to have all the isolation, all of those things. So we have things like fabric manager. We have a set of rules that are there, so that, for example, this server might have a deadlock or whatever, it might be hung. Doesn't mean the rest of them are getting hung, because it should not hang, because you have a common set of resources here, pooled set of resources. So we defined all of those things along with things like fabric manager, API, all of those things. And of course, security is always an ongoing thing that you always try to improve upon. So we made significant improvements there. But that's basically the third challenge that we solved, is around the stranded resources in the data center. 3.0 came along, and there are a few things we did. One was, of course, we always, if there's a speed increase, we will go with the speed increase. So, we doubled the bandwidth. By the way, we paid zero latency adder for going from NRZ to PAM4. We are very sensitive to latency. We went through a lot of innovations to make sure that that happened. But, from a challenge point of view, of course, that speeds and feeds are there. Everybody needs them. Fine-grained data sharing is what we did. And we did that by doing two sets of things. One is, of course, we increase the size of the system that you can construct. The first CXL 2.0 was up to a single switch, right? Whatever was the fan out. Here we increased it to 4096 endpoints that you can connect together. And we made them to be effectively the hierarchical tree topology that is mandated, that was mandated up until now. We broke that, and it's like a fabric thing. So you can have multiple entities, multiple ports that are interconnected to each other. We have the notion of unordered I/O. A lot of these things. We have the notion of shared memory across coherent shared memory across multiple independent domains, right? Server domains. So that's basically what we did. And it is to effectively make sure that we are ready to be a backside fabric to supporting large distributed system. And that's what we addressed with CXL 3.0. So things like direct peer-to-peer access, for example, not everything needs, even if it is coherent memory, not everything needs to go through the CPU, through the host processor. We introduce things like back invalidate, all of those things, right? We introduce things like unordered I/O. So these are simple constructs, but they fundamentally change the way load store I/O is going to evolve going forward, not just for CXL, but also for PCI Express. And make them to be much more readily fabric ready. Right. So that's the third one. Now, how well are we doing as an ecosystem? So this is a snapshot in time. I did sometime in the end of April. So membership was 255 plus, right? So product wise, I say here 3 compliance events. By now it is 4 because May 4th has come. I haven't updated my slide, but up until the end of April, we had 20 CXL 1.1 devices. Each of these is a link you can go click, and these are all public domain information. As you can see, there is a lot of type 3 devices. So, so memory is a real challenge. So a lot of them are doing type 3. Okay, that's almost a gimme. And then there's significant software development happening. So let's look into type 1, type 2. The initial intercepts that we see are around things like the smart NIC, especially for a lot of high frequency trading kind of applications, and also VM migration, right? I mean, there are papers. This one is a paper. You can go look into it. This one is one of the website where they talk about how they take advantage of coherency semantics, the low latency, in order to deliver the type of throughputs that they're looking at. Type 3 memory, there's plenty of them. Yes, as I said, the bandwidth, it's an additive bandwidth, so that helps with the loaded latency. The individual latency does go up, but that's similar to a nearby CPU socket latency. And there is we have a tutorial there that you can click on that. And you'll see basically as you would expect, right? I mean, the curve starts like this with only DDR, whereas with CXL, it's going to start a little higher, but then the knee of the curve moves way further up, which is very intuitive, right? That's what you would expect. Pooling, we have, so CXL 2.0, there's a lot of POCs that are looking really promising. So there was a Pond paper that basically had the VM elasticity memory demand, and they are going to have an update. I'm not at liberty to talk about, although I know that about the results. It's an Intel and Microsoft joint project. I'm still not at the liberty to talk about it, but the initial 9% DRAM savings, we are looking into significantly higher amount of DRAM savings, which is again what you expect, right? As people tweak on things, you make changes to the hardware, you address some of the challenges, and that's basically what it is. And it is direct connect, right? It's basically the model, so the switching cost will not be there. And then the other thing is around the database, right? SAP and Intel, we have done a lot of analysis, so we saw that not there is a lot of benefit in terms of, even there is elasticity, and TPCC has pretty much negligible performance impact, and there is a paper there that you can take a look at. Speeds wise, 128 gig is coming pretty soon, 2025. And sharing and fabric, it is still work in progress, because 3.1 came last year, so these things have a pipeline of things too. So it will continue, but things are looking pretty promising at this point. So now, where do we see, and how do I see CXL evolving? It's basically, we are going to go beyond the node, right? I mean, the thing is that you're going to have compute resources, you're going to have accelerator resources, you're going to have storage resources, you're going to have memory resources, you're going to have an infrastructure processing unit or smartening or whatever you want to call it. And they all get connected through a load store fabric CXL. So that way you can build this composable system. You can do message passing. You can do all of those things, right? You can build your HPC systems using CXL fabric, right? I mean, that's really where things are headed. That's what we are working towards. And with UCIe, what happens is that we solve the reach problem with co-packaged optics with very low latency, right? The challenge with the optics is going to be around the cost of it and the availability of it, but even it's not a question of if, it's going to become when we are going to have a wide scale deployment. We're going to then have a lot of bandwidth that basically cross across a rack and a pod, and now you've got resources that are accessible from anywhere, and you can really do these composable systems, collaborative computing kind of systems that multiple servers can work together, and that's going to unleash more innovations going forward. So I know that was that was a pretty quick walkthrough of these technologies. By the way, there is a tutorial that we have which goes through these things in a lot of detail. You can it's an archive, so you can take a look at that. But with that, I'll pause it, see if we have time for one or two questions.
Sure. Let's thank the speaker. Okay, we are right on time. We have time for one question. Okay. That is not me. So we have time for one question. If not, we can move to the next one. Any questions, folks? Yeah.
So the CXL, there has been a lot of discussion going on. I know it will be beneficial for latency. How about for bandwidth?
Yeah, so the bandwidth is an additive bandwidth, right? So if you look into the bandwidth, and it's, as I said, right, if you look into the bandwidth comparison, for instance, if you're doing using it as a, primarily people today are using it as a memory bandwidth expansion. Okay. The pin efficient per pin, right, the amount of bandwidth you get with CXL is 10 times more than what you will get in DDR. So it's and then with the doubling of data rate coming every 2 years or 3 years, it's pretty much it's a no-brainer, right? That you're going to work come out ahead in terms of the bandwidth. In terms of the communication bandwidth between CPU, GPU, or CPU AI accelerator, or as a backside fabric, there are comparisons now, for example, with like, the networking side goes a lot faster in bandwidth. But if you look into the fundamental construct, right, it's the same kind of service, it's the same kind of things. It's basically the channel reach versus whatever you're trying to do, right? On the motherboard, if you go for that distance, about 10 inches on the motherboard and then an add-in card, that's the construct of the platform. That's basically what constrains the frequency increase. If you put like a cable topology, on the networking side, we can easily keep doubling the bandwidth even faster. So there's nothing fundamentally, it's the same kind of infrastructure, and doubling of the bandwidth doesn't necessarily double the bandwidth density. That's a misconception. In general, we have done studies which shows that you do get about 1.3x, not 2x, everything else being the same from a silicon area point of view. I think what happens is that your channel reach on the platform, it reduces significantly, right? So that's the bigger challenge, right?
Thank you.
Let's thank speaker again.
Yep.